Okay. Yeah, it's 8:30, so we should begin. Hello, everyone, and welcome to the Physical Review Journal Club. My name is Chao Chao. I am the Associate Editor of Physical Review Applied, and I'll be your host today. We at APS have established our Journal Club series of talks to highlight some of the very interesting research that appear in our various journals, and to provide a venue for authors, especially the early career researchers, to discuss their work interactively with the community in a relaxed setting. So today's talk will be on a PR applied paper from January that we chose as an editor's suggestion. Topological Solitons Make Metamaterials Crawl by Bolei Deng and his colleagues at Harvard University. Bolei will be our presenter, and our moderator will be Professor Bolei Deng from Nanyang Technological University in Singapore. Before we get started, I have some brief announcement. PRX Energy is our newest member of the Physical Review family. In much the same mode as PRX Quantum, PRX Energy is a high-impact, multidisciplinary journal spanning many research communities and subjects, all centered on energy research and technology. It's a fully open access journal, and for the rest of the year, we're waiving the publication charges. PRX Energy is open for business, and it has been publishing papers since April. Zoom etiquette. Please be sure to stay muted until the moderator calls on you. And please use your real name. You can set it by right-clicking on your handle in the participants list, which I'm showing here. We will hold the questions until after the talk, but feel free to enter them in the chat window as they occur to you, or just raise your virtual hand during the Q&A session. So without further ado, I'll pass the microphone to our moderator, Bolei Deng, who will tell us a little bit about himself and the context of the work at hand. Professor Deng.
Right. Okay. Hello, everyone. Okay. Thanks for joining us for this journal club. My name is Bolei Deng. I'm from Nanyang Technological University in Singapore. Okay. I'm affiliated with the School of Physical and Mathematical Sciences. So we do some research that is related to this paper. Okay. We do topological waves as well as acoustic waves together. So for this presentation, this is the recently published paper published in Physical Review Applies a few months ago. The title is Topological Solitons Make Metamaterials Crawl. So later you will see a metamaterial that can move like a robot. Okay, I think it's the first time that topological waves is combined together with a robotic motion control. Okay. So for the presentation, it will last roughly 15 minutes, right? And later we will take questions. Okay, we have plenty of time to take questions. So if you have a question, you can type either in the chat function or you raise hand. Okay. All right. So Bolei, if you're ready, you can start anytime.
Okay. Thank you, Chao. Thank you, Bolei, for the introduction. Let me share my screen. Okay. Okay. All right. All right. Thank you, everyone, for coming. A little bit about myself. I graduated from Harvard last year, and and I'm now at MIT as a postdoc associate. I'm co-advised by Professor Wojciech Matusik, which is doing artificial intelligence and machine learning. And I'm also co-advised by Xuanhe Zhao. He's from mechanical engineering, where I'm working on ultrasound, which is some kind of application of metamaterial to healthcare. So today, my talk will be based on our recent paper in PR Applied. Oh, I think someone is speaking, maybe. Oh, okay, no, it's fine. Okay. So today my presentation will be based on our recent publication at PR Applied, which we use topological solitons to build some locomotion robot. So let's start with some a current example of locomotion robots. So normally when we talk about locomotion robots, what we think will be many actuators and a very complex control panel. You typically need some central processing unit to coordinate all the actuators. They need to work coordinately in order to move forward. And normally they are very vulnerable to failure because even one actuator break can disable the whole system. Recently, there is a step forward towards a vulnerable direction, which is this particle robot, also from Harvard. This is a Nature paper where they use they use the communication between those so-called particles in order to achieve some group activity, so the whole thing can move. But still, in this kind of system, each particle has its individual sensor, actuator, and even a processor. So the cost of fabrication is still very high, and also the size of this robot is very large. So our motivation here is, can we design some locomotion mechanism that is not only robust, but also requires very few number of actuator or even a single actuator? So can we embed it all the, the sequential or the motion of locomotion into the material itself, other than using some kind of CPU to control all the actuator? So following this direction, we start to build our structure. So the structure starts from a very simple unit cell. So this unit cell consists of 4 crosses. The crosses can be regarded as rigid. And at the same time, the hinge is very soft, is elastic. And we put a rubber band, and we put a rubber band around the unit so that it's forced into a bistable energy landscape, so that the whole unit becomes bistable. This is because when you trying to switch from one state to another, you have to go through a stage where the rubber band are elongated. And you can very simply write down the energy, the potential energy of the system, if you regard the crosses as rigid. And then you can see this is a double well kind of energy, which means they are bistable. And you can do experiments to verify that the energy landscape is indeed this bistable form. So with the unit, what we can do is, if we connect those units together, for example, 3 units by some kind of what we call intershim, which means they connect one unit to other. So when we do that, when we flip the first unit, we find there is a sequential flipping from left to right because of the existence of this intershim. So what this intershim essentially do is the unit now start to talk with each other. So the change of state of one unit can propagate through a second unit and to the third unit. So you are essentially sending kind of like a pulse from left to right. And in order to do it more clean, we assemble an actuator to basically, instead of using hand, to initiate the state change of the first unit. Here is our simple actuation design. So what this actuator does is simply to flip the first unit. And by doing that, we can carefully monitor what happened when we flip the first unit. We find that there's something propagating from left to right. There is for sure a sequential activation of the unit cells. And we find that this the property of this pulse also depends on how strong the interacting shim are. For example, when the shim becomes longer, it will be weaker, so that we can see the transition is a little bit sharper. So in order to study this more carefully, we build a very simple model. So the model is actually an extension of the previous one unit cell one. So where we sum up all the energy of each unit and plus the interacting energy. This is the energy stored in the intershims. And then we use the Lagrangian mechanics to solve this problem. This can be transformed into a set of ODE, which can be solved by MATLAB easily. So after solve this equation, we find that the wave has two kind of a degree of freedom. One is rotation, which is the rotation of each unit cell, the change of state. And at the same time, as the crosses rotate, it also extend because the size of the square becomes larger when it extends. We compare the simulation results with experiment and find the matches pretty well at different time points. And we go one step further to rewrite everything. So we have the ordinary differential equation. What we can do is we can continualize those equations to the partial differential equations. So those two equations you can imagine they are like the governing equation of the whole system. Interestingly, this gives some kind of solution which is called topological vector soliton. So this equation we can transform it to a nonlinear Clay-Golden equation, which under certain parameter range, it gives you a topological vector soliton solution. So why it's called topological vector soliton? So it's actually, the idea is pretty simple. If you have the units on the left in, for example, the minus phase, and you have the units on the right in plus phase, then this is, you can understand this as a domain wall between two phases. So as long as this unit is minus, this unit is plus, there has to be something in between. And this is protected by the topology of the structure. This is a little different compared to the typical acoustic topological waves, because this is kind of in the nonlinear region, and the topology is more about the topology of the structure. So that we know this kind of wave is quite stable because it might stuck in between, but it can never die. As I said, as long as you have two sides fixed phase, the center, the topological wave will always exist in the center. But as I said, sometimes when the shim is very weak, for example, here, it's longer, and the unit is long, there is some kind of case where you can see we flip the first unit, but the last one does not move. This is because the wave is stuck in between. But at this time, when we decrease the number of units, the wave can propagate through, although it's barely propagate through. And then we use our theory and this simulator to kind of systematic study this this behavior, like when will the pulse propagate all the way through the end, and when the pulse cannot propagate all the way through the end. And we find that this blue area is when we do simulation, and we find that the last units are not flipped. This yellow area is when we do simulation, we find the last units flipped. And it matches very well with experiment, which is denoted by the circle and the crosses here. And also we have we can use our continuous theoretical model to predict this boundary. So everything matches pretty nicely. So it's kind of, we understand this behavior quite well. So we have this topological soliton, but what relation it is to the locomotion robots that we were trying to build. So this topological soliton actually has a feature because it's actually a vector soliton because it has two components. So as it's flipped from one end to another, it's not only creates rotation, you see each unit cell rotates during this process, but also with this rotation, there is an extension because the cross simply becomes, when the cross becomes straight, it becomes a little bit larger. So we know that extension is essential for crawling robot because you need to extend somehow, somewhere in the robot in order to move forward. And the rotation actually is also a key element because it can be used to change the friction of the structure to the ground. So in order to do that, what we did is, there are many other ways, this is just one way, is we attached a few wheels to the bottom of our unit cell. So the role of wheel is actually to change the friction with the ground. You can imagine when everything is rotated, when the cross is rotated at a certain angle, the wheels locked with each other. So the friction between the ground is very high. As you can see, we incline the platform to a large degree and it do not roll away. But on the contrary, when the angle is 0 degree and it's very easy to slide away at a very small angle. So that means the friction between the ground becomes very small when the angle of the cross is close to 0, as showed by this plot. Okay, so with this, we are ready for our first locomotion robot, which we attached a actuator as the first unit, and all the units you have wheels beneath. So the mechanism is actually pretty straightforward. Is that when you flip the first unit, you can see the first unit become the angle of first unit becomes 0. And as we said, when it becomes 0, the friction becomes less. And as it becomes 0, it's also expand. So when it's expand, it will move leftward a little bit, and as the unit keep flipping, it's going to if this is plus phase, it's go to a minus phase where the friction becomes larger again. And at this time, because the wave is propagating towards right, and the rightmost unit cell becomes 0 angle, and at that time, the friction of this unit cell becomes small. So this part becomes a new anchor point. And at the end of this cycle, the whole thing shifts to the left. So you just keep repeating this process. And the topological, what the topological vector soliton did is it creates the extension and change the anchor point at the same time. So that you only need one actuator to do this complex movement, because everything is already embedded into the material itself. And this process depends on the step length of the locomotion, depends heavily on the shim. So sometimes it's climbed faster, sometimes it climbs slower, depending on what is the interacting shim, the strength of the interacting shim. And our discrete model, which is our simulator, can also simulate this. And we can give a prediction of the step length as a function of hinge length, which is showing here, hinge length. And we can compare with experiment, find it matches pretty nicely. And because in simulator, we can run different cases. So this can really give us a very good guidance for robotics design, where we plot the step length, where the more red the design is, the better the performance is, because the step length becomes larger. So it depends on both the hinge size of the interchain and also the chain length, because longer the chain, the behavior will be different. And this actually serves as a guidance for future design. If you want to design a certain crawling robot, you can just pick from this graph. And in the paper, we explain more nicely about how this 2 white lines come from. They are actually from the continuum model. And we have some ways to even use theory to enclose the workable range of this locomotion. Okay. And so with the locomotion works, we start to do something more advanced or more interesting, where we think we can attach 2 actuators to a longer chain. So when we have 2 actuators, what we can do is with the same structure, we can control the phase lag between those 2 actuators. So the same structure can move left, right, or stay. So so all the structure are the same structure. We're just controlling the phase of 2 actuators. And another advantage of this mechanism is that you have a structure. Even you cut the structure in half, each of them can still work individually. So imagine you have a structure, and when you cut, as long as there is one actuator inside this material, the material can move. So it's pretty robust. And later we extend this concept into 2D, but 2D one is still very preliminary. So we did only a 2x2 unit cell. So with this 2x2 unit cell, we can do a different trajectory by controlling the phase lag between the two actuator. And you can rotate, advance, and even do inside works. So this is a very bad summary slide. This is actually a poster I used to do in another conference, but this probably gave you a reflection of what was in this slide. So we designed a unit cell that is bistable, and by connecting them together, we find the structure supports topological vector soliton. And the soliton has a rotation component and the extension component. And the rotation component can be used to change the friction with the ground, which can actively change the anchor point of the robot so that the robot can move forward with only one actuator. And in 2D network, you can achieve more complex motion. So using this metamaterial, we are kind of trying to build a robotic material that can transform a single input into complex output. The metamaterial is designed for locomotion so that every complex coordination is built in the material itself, not by the actuator. And also because this is the whole thing is kind of a material, so you can cut it in half and it still can work individually. And we also developed the simulator and the theory that can accurately describe the system so that for future design, it's easier to identify the optimal designs. And also, lastly, we are using wheels here, but we are not necessarily using wheel. We can use a blade, for example, for skating robots or moving sand, or we can add some paddles so that it can be designed into a swimming robot. So the concept is that the whole mechanism is embedded into the metamaterial itself, other than the actuators. So with that, I want to thank my co-authors, Dr. Mohammad Zaneti, who did most of the testing of the robot, and Dr. Antonio Forti, who is now actually a professor at the British now, and my advisor, Professor Katia Bertoldi, who is very supportive through this work. So with that, I would like to take the questions. Thank you.
Thanks, Bolei, for this very nice talk. I think we are open for questions. You can type either in the chat or you raise hand directly.
Yeah.
I think we already have a question from Matt.
I can actually see that from chat.
Yeah, but better to I will read it out. Does a longer shim, which is the weaker coupling, simply correspond to more efficient dissipation of the energy required to flip the state, or is it more complicated?
So that's a quite good question. So when you have longer shim, so here is a let me go back. Sorry, let me go back to the slide. So actually, there is two extreme. You can see in the plot here. When you are too long, when the shims are too long, why this is 0 is simply because when you flip the first unit, the last unit does not flip. And then when you flip the first unit back, the whole process is reciprocal. So by reciprocal, it means it will go back to wherever it is. So if you keep doing, you keep flip the first unit back and forth, it won't do any locomotion because the whole process is symmetry. But when the shim is too long, then everything moves together. So it's also kills the non-reciprocal reciprocity because there's no longer a directionality in the system. So as that being said, it's kind of a little bit complex, and the shim cannot be too long and cannot be too short. Yeah, does that answer the question? I'm assuming yes.
Yes, thank you.
Oh, thank you.
Okay, so any other questions?
Yeah, I have one.
Go ahead.
Yeah.
Hi. Bolei, I was reading your paper, and at the end of it, you mentioned the efficiency of the locomotion mechanism. I was wondering, and you cited, I think the value is around 3%. Have you compared the efficiency of this mechanism with like organisms in nature that like move similarly, like maybe like a caterpillar or something that like with extension and rotation?
I haven't, but because the point here is actually not efficiency. So we characterize the efficiency, but the efficiency is not our goal. But I admit the efficiency of this robot is not the highest in the field. So what we're trying to do is just build something more robust and maybe propose new locomotion strategies. So the efficiency is not ideal in this case, because as you can see, most of the energy is dissipated through for example, the friction between the wheel with the substrate, and through the friction, the damping in the rubber band and the damping in the joints. So that's why we have like only a few percentage of efficiency.
Totally. Thanks, Bolei.
Yeah, thank you.
Okay, any other questions?
I have a couple if nobody has one.
Yeah, go ahead. Go ahead. Okay.
So I know that you guys did an imperfection insensitivity study, which I thought was really cool. Imperfection.
Oh yeah, thank you.
Of course, yeah, imperfections are a fascination of mine. I was wondering if you ever played with, so I know like, the bistability of the energy landscape makes it flip, repeatably. And that, did you ever look at introducing some kind of imperfection in the form of like a change to the energy landscape? Like maybe it's like an asymmetric, it's like accentuating the asymmetry of one of the potentials,
yeah.
And maybe making it like quartic.
Yeah, we actually did that in SI, exactly what you said, when the energy landscape is asymmetric. So if there's no other question, actually I can quickly show you.
Yeah, go ahead.
Okay.
Yeah.
Okay.
We have plenty of time.
Okay, great. So yeah, what you said is exactly what we did. And so probably you will be happy with the result here. Let me try to find it. So what we did is, but what we were doing is in simulation, of course, because in experiments it's very hard to design the asymmetry of the energy landscape. So let me try to find. Oh yeah.
Well,
yeah.
I think you can simply use an asymmetric cross, right?
Yeah, that's true. And also we can, yeah, right. So if you can make the cross, not so one arm is longer than the other two, then you can make it. Yeah, that's right. So here we designed some energy landscape that is in simulation, what we did is we assigned different initial angle, because in experiment the initial angle is always zero. So we fabricate a cross and then we add a bend. But in simulation we can add different initial angle. What that does is actually make the energy landscape asymmetric. So when it's asymmetric, it's actually easy to imagine. What you will have is you will have one step longer, one step shorter. Because when you flip from higher energy to shorter energy, you kind of emit more energy. And then the step length of that flip will be longer. And when you try to flip back, because you need to overcome this energy, so the step length becomes shorter. So you can see this graph actually shows that when the bias angle is 0, 2 step the same because plus minus symmetric. But when the plus minus becomes asymmetric, you can find the maybe the caption here is wrong. From higher to lower, the step length becomes longer, and the other step becomes shorter. And until you reach a certain point, probably you are unable to flip back, because the energy difference is too large. The coupling shim is not so strong, or in some case, even this is not stable anymore. Yeah. Does that answer your question?
Yeah, absolutely. That's really cool.
Oh yeah.
So you mean this train can make a turn, bend either left or right?
Yes, but in order to do that, you need to actuate. My understanding is that this mechanism can, for example, for this kind of earthworm robot, they need to control every muscle and use a central control panel to squeeze sequentially in order to make a motion. But we only need one. But my understanding is that one actuator will only give you one moving mode. If you want to move both right and left, then you need 2. And yeah, something like that. So we just use this mechanism to eliminate the need for this artificial sequential movement. But if you want to achieve complex motion, you need more input.
I have another question.
Yeah.
As I was looking at it in the beginning, I was wondering, I think I know why you have it, the transparent elastic band that keeps it in the square shape. That gives it some rigidity to the unit cell, I guess. But I wonder if you actually need that, if you make your hinges out of the right special material. Could your hinges be stiff enough that you didn't even need the elastic band?
But unless your hinge itself is bistable, if without the band, how can you achieve it? Also, the band is actually for the bistability, not for the rigidity of the sample, right? So even without the band, the whole thing is quite stable, no problem. But the whole thing is not bistable. So the only stable point, if without band, is this stage. You see when the crosses are fabricated, they look like this. Only when you put on the band, it looks like this because the band is trying to squeeze it.
I understand that. Yes. Okay. So it's, yes, that all right. That makes sense to me. It's the force that has to be resisted in either direction is provided by the band. Okay.
Yeah, right. So only when you create a band, you can create this double well, because both those two faces, the band are at the minimal length. And in order to change from one to another, you have to go through a state where the bands are elongated. So that's why you see this peak here. Yeah.
Right. Okay. Thanks.
Thank you.
All right. Any other questions?
Well, I have one more. Just to
yeah, sure.
So in this particular experiment, you've used flat shims. I mean, it might be completely impractical, but I was wondering what your thought, or if you ever thought about using shims with curvature, kind of like like those snap rather catastrophically. I was just wondering if you'd ever thought about imbuing any of the ligaments with curvature.
You mean
like a tape measure kind of thing?
So you mean the shim itself can snap?
Yeah.
through to stable state. Oh, I see what you mean. So it's kind of, there is a curvature in the shim. So that's when you flip it, there is a, I see. Probably something will change. The landscape will change for sure. But I don't know what, I think it's probably serves similarly as a rubber band, but if it's a snapping mechanism, I see. So if it's a snapping mechanism, my guess is that the energy landscape will be different when you flip from left to right compared to right to left. Because for snap, as for my understanding, you need to go a little bit further to the other end in order to activate the snapping. Right, you need to go a little bit over the central point, and when you snap back, it's something like this probably. I don't know if it's beneficial or not, but certainly using this mechanism, you can create a steeper descent in your system. Yeah,
that was my thought.
Yeah,
maybe narrower, but
yeah,
I appreciate it.
Could be interesting, I think. So you're kind of loading the system slowly, and then when you emit the energy, it's very fast.
Yeah.
So probably it's, yeah. I think that's a good idea.
Thanks. Awesome. Really cool.
Thank you.
Okay, we also have a question in the chat. Right. Is there something unique to the square unit cell? For example, what the pentagons or triangles also buckle and have bistability?
Yeah, there's nothing special about square unit cell, and that is actually something we can think. I was thinking that maybe we can, in the future, we can 3D print the whole thing, but it need to be carefully designed. So many 3D printers now can use 2 different materials. So if we can 3D print that, we can quickly build a material out of this. And in that case, we can start to think, is the square optimal? We can actually build, because here is square, because I'm building this using Legos. This is the only option with squares, and the squares are the easiest for sure. But if you can 3D print the whole thing, it doesn't need to be a square. And as a matter of fact, it doesn't even need to be the same over the space. So some part can be some triangles, some part can be some polygons, and some part can be squares, all depending on what the task is. So you can even design the whole structure to fulfill a certain task by designing the size and the topology of each connection. So yeah, there's nothing special about squares. You can, principally, you can do it with anything. So the key element is actually here. So I can draw it. So it's actually the same as snap a beam. We just make it in 2D. So you can see this here. This kind of look like a bent beam, right? A buckled beam. And it can snap to right, as case here, and it can also snap to left. So this is the source of the bistability. So this 2 arms can snap to left and can snap to right. So as long as you have this kind of structure in the system, principally it can have bistability. And it's not necessarily using cross. So you can connect. So here each element connect 4 arms, but you can connect different number of arms. It doesn't matter. Yeah, but that's a very good question, very inspirational.
All right, any other question?
I was wondering, do you think it's possible to get around the need for another actuator to turn left or right just by choosing like a different shape for the face that between each of the crosses or something, like making it a tri-stable landscape essentially rather than bistable, for instance. So you could, go halfway, come back, go halfway, come back.
That's a great question. I never think about that, but my intuition is if you are using the similar system, so the mechanism here, if high levelly speaking, is actually you have a wave propagate from left to right, and the robot move from right to left. So this is the same as the motion of earthworm. It's called peristaltic wave, something like that. So as long as you are using this mechanism, I think it's kind of probably hard. So if you actuate here, if you actuate on the left and you are trying to move in the same direction the wave goes, unless you change the moving mechanism, or you can find some way to achieve this. Even your actuator is here, but somehow you can initiate a wave propagate from right to left. So this I don't think it matters if it's bistable, tristable, or multistable. It's just if you think it very high level, it's just the directionality of the system and in which direction it moves. Does that make sense?
Yeah, I think so. I guess it would have to be some sort of like asymmetrical setup.
Yeah, exactly. Yeah. Or I don't know if that will work. Like change the frequency of the flipping. So in the SI of this paper, we actually studied if you actuate at different speed, the performance will be different. So what we all show here can be considered as quasi-static because the actuation is very slow. But when your actuation becomes faster and it's the dynamics start to play a role, the behavior will be a little bit different. Yeah, but we didn't study that part in this work.
Does that mean you can sort of launch like a shock wave if you go fast enough, if that makes sense? Like the...
Yeah, so if you go faster, it's more like a real wave, right? It's really propagating. And in that case, one thing is that you can actuate longer structure. For example, in this case, when this is 5, we cannot go over to the end. But you can imagine if you flip the first one really fast and pump some dynamic energy into the system, it's possible to make it go through. So this is just an example of how flipping fast will change the behavior of the structure. I'm not sure if you flip fast or flip in a certain pattern, you can even achieve different locomotion mode. That part I'm not sure. I'm just saying the dynamics could play a role. Does that make sense?
Yeah, absolutely.
Now we have a question in the chat. Blocked solitary waves or the compactons or the localized waves can be useful for your system.
Oh, compactance. I look into compactance sometime, but I'm not sure what exactly this means here. But localized wave probably will be useful. I can answer the second question. Maybe maybe Marius can explain to me better about what block the solitary waves is. But I can answer the second one. So localized wave, I think it can be interesting because in our case, it's very easy to stop the propagation of the pulse because you simply fix 2 ends and the pulse will be trapped in between and the pulse will always be here unless you free it from one end. So by saying that, you can actually control the position of the pulse by like controlling the angle here, and you can kind of imagine pushing a bubble inside your system. And if you can carefully push this bubble, probably you can reach a more complex motion. So this is 1D. Imagine a 2D. You can trap some kind of this topological soliton, like a bubble inside the 2D structure. And then you have a few actuators inside this structure. And by actuating differently, you can push this thing toward different direction. And because this thing not only change the extension, but also change the friction with the ground. So probably play with the localized wave, you can do some more complex motion. That's what I think. But for the compactance, I'm not super clear what it means in this context. So I don't know.
Very good. Okay, so we do we have other questions from the audience? All right, I think if there's no other questions, okay, I think probably we can finish over here. And of course, if you have other questions, I think you can also email, send your questions to Bolei as well.
Yeah.
Okay, so
All right. Yeah.
yeah. So on behalf of all of us here at APS, I'd like to thank everybody who attend this event, especially Bolei and Baila, for a very stimulating discussion of this cutting edge work. So as I have posted in the chat window, and I'm going to post it again, don't forget to check our webpage for the next journal club, and we will see you then. Goodbye.
Bye-bye.
Thank you.
all.
Thank you, everyone.
Thanks, guys.